Hello dear students, today I will discuss about Lagrange's method of undetermined multipliers. That is for finding a stationary value in the case of finding maximum and minimum values of function of several variables. Several variables means multivariables, more than two variables, three, and more than one variable, just two variable, three variable, and etc. So if we are having function, suppose function of x, y, z, function of three variables. In here, these three variables are not independent but connected by some relation. Maybe one relation, two relation, three relation. Suppose there is relation. This is our function. Suppose this is our function, and here x, y, z are connected by 1, 2, 3. Maybe x, y, z equals to 0. X, y, z equals to 0. Phi 3 x, y, z equals to 0. That means what? Where if we have u equals to function of three variables, and these three variables are connected by one relation, maybe two relation, maybe three relation, then how can we find for stationary points where maybe maximum, maybe minimum this function? So this method is especially for finding the stationary points. How can you find the stationary points? At that point function is maximum or minimum. In this method there is a drawback that we cannot determine the nature of the stationary point. We can find a stationary point by using this method whenever the variables are connected by some relation also given. Okay, so this method gives the technique for finding stationary points, and nature of stationary points, whether at that point function is maximum or minimum, it cannot be found by this method. Okay, for that, for determining the nature of stationary points, we can use we can consider physical condition of the problem, physical consideration, because what type of questions are there, and what will be the physical condition, geometrical condition. By using that, maybe geometrical condition also, by using geometrical condition or physical condition from the problem, we can decide whether the function is maximum or minimum at the point of stationary point. At the stationary point, whether function will be maximum or minimum, we can use geometrical condition or physical condition of the problem. Okay, if single relation is given, then we can determine the nature of the stationary point by using previous method. Just like from here we can convert one of the variable in terms of other two variable and put here, then we can get a two variable function ultimately. Okay, so here from here we can write z equals to function of x and y, and we can use here that is function of x, y. In place of z we can write x and y. So finally this will be what? Function of two variables. So we can find maximum minima nature of the stationary point as usual previous using previous method, that is rt minus s square and etc. If single relation is given there, then okay. If not single relation, or in the case of also single relation, we can use geometrical and physical consideration of the problem for finding nature of the stationary points, whether it is for maximum or minimum. Okay, so this method is useful for finding stationary points. Okay, so here what will be the formula for this method? Lagrange's equations. What are the Lagrange's equations for solving and getting stationary points? So here, suppose we are given, let u equals to function of x, y and z, where x, y, z are connected by the relation phi x, y, z equals to 0. There is a relation between x and y, x, y and z. This, in this value, this is function of x, y, z, and this x, y, z are connected by this relation. Suppose this is equation 1 and this is equation 2. There may be more than 2 relation, connecting relation. Suppose here single relation. Then Lagrange's for the undetermined multiplier method gives equations for solving and getting stationary points, just like using total differential formula. Here, let this, and we have to find for maximum and minimum value of this. For maximum or minimum value of u, we have what? Necessary condition, we know what? Del f by del x equals to 0, del f by del y equals to 0, and del f by del z equals to 0. These are the necessary condition for existing of extreme values, maximum or minimum value. So del f by del s, del f by del y, del f by del z, all are 0. So from here we can connect this, we can write a relation, because we are making equations for finding stationary points due to Lagrange's method. What? Here we can write del f by del x dx plus del f by del y dy plus del f by del z dz is equals to 0. We can write this, because this is 0, this is 0, this is 0. So if this is right, then we can write like this. So it means what? It means df equals to 0. df equals to 0. Total differential. Okay? Also, using total differential, we get from 2 that from 2 this function of x, y, z phi. So total differential. What total differentiation? Differential d phi. Because right hand side is 0, so d phi equals to 0. So d phi equals to 0. So also you can find here from here d phi equals to 0, and d phi will be what? D phi means total differential of this what? Del phi by del x plus dx plus del phi by del y dy plus del phi by del x y z dz equals to 0. D phi total differential, d phi equals to 0, right hand side 0. So d phi equals to 0, that is del phi by del s dx. D phi means differentiate it, total differential. Del phi by del s dx, del phi by del y dy, del phi by del z dz equals to 0. Here d phi equals to 0. So we can write like this also. Clear? Differential, total difference, taking total differential on both sides. Okay. Now we get two equations here. This and this. That this is equation third, this is equation 4. We are trying to find a stationary value for maxima or minima for extreme values of this function, where these variables are connected by this relation, single relation. So this is two equation 3 and 4. Now we make a relation due to Lagrange's undetermined multiplier, because one multiplier we use here. Whenever one relation is given, we use one multiplier. If two relations are given, two multiplier. Three relations given, three multiplier can be used, and that multiplier is used for finding stationary values. Okay, so here now we multiply 4 by lambda and add to equation 3 we get. Clear? Now we multiply 4 by lambda, this equation getting from this relation, by lambda, and add to this equation, that is df plus lambda d phi equals to 0. We get this. So this provides us Lagrange's equation. Here df, that means this, d phi, that means this. Now this combination gives this plus lambda into this into dx. So this equation gives del f by del x plus lambda into del phi by del x dx plus del f by del y lambda del phi by del y plus dy. This equation gives plus del f by del z plus lambda del phi by del z dz equals to 0. This means what? This equation will satisfy if separately this is equals to 0, this is equals to 0, this is equals to 0. Okay? Which gives us, so now we can write for maxima minima of u this equation, this, which gives means this. Okay, what? This is equals to 0, this is equals to 0, this is equals to 0 for satisfaction of this equation. So del f by del x plus lambda del phi by del y equals to 0, del f by del x y lambda del phi by del y equals to 0 and del f by del z lambda del phi by del z equals to 0. This three equation we get. Okay. Now this three equation can be solved because function is given, so you can find del f by del s, del f by del y, del f by del z, and phi relation is also given, so you can find del f by del x. This are separately 0. X, x, y, y, z, z. And del f by del phi by del y, del phi by del z you can find from the given relation. Okay. By using this three equation, one, two, and this is 4, 5, 6. Okay, in between there 3 and 4 equation was there. So these three equations are known as Lagrange's equation, which gives this. So for maxima or minima of u, we have this. Okay, we have this. This equation are known as Lagrange's equation. We have the Lagrange's equation. Lagrange's equation. These are the Lagrange's equation. Okay. This three equation and 2. This, and this can be solved. Okay. It can be, this can be find from here, this can be find from here and put here, then equation 1, 2 with the relation 2, 4, 5, 6 can be solved, and we can get by solving 4, 5, 6 and 2, we can get the values of x, y and z, which will be required stationary points. Clear? These three equations can be solved with this relation. 4, 5, 6 and 2 can be solved, and we can find the values of x, y, z, and this values of x, y, z are stationary points, gives stationary points, which will be required stationary points. So this is the method for finding stationary values. In the Lagrange's method, Lagrange's equations are this. With this equation, the relation we can solve and find stationary points. Okay, so in this method, stationary points finding is main thing, and whether stationary point gives maximum value or minimum value cannot be decided by using this method. We use geometrical condition or physical condition of problem for finding nature. Okay, and also if single variable, then we can convert it into variable function and then you can use previous method. Okay, so here lambda is undetermined multiplier because its requirement is not, but by using this we find value of x, y, z. Okay, so similarly if there are two relation as given, suppose phi and also there is another relation given, what, psi, suppose two relation psi x, y and z, suppose another relation is also given, then we can extend this formula as what, this lambda 1, two multiplier will be used if two relation are given, lambda 2 del psi by del x equals to 0, lambda 2 del psi by del y equals to 0, lambda 3 del psi by del z equals to 0. In case of here, suppose another relation is given in x, y, z, two relation, then they become three relation, then also lambda 1, lambda 2, lambda 3. And for finding value of x, y, z, 1, 2, 3, 4, 5, 5 relation are there. Then by using this relation we can get value of x, y, z. In between lambda 1, 2, 3 are used. Sorry, this is lambda 2, this is lambda 2. Two undetermined multipliers are required. Okay, similarly by 3 relation, then you can extend also. Okay, now for finding this relation we can also write it as, just we write what, d f plus lambda d phi equals to 0. If we write relation like, suppose this is given function f plus lambda of phi and it is denoted by capital F. If we denote it, if we denote this, denote like this, then del f by del x, f is also a function of x, y, z. So del f by del x means what? Del f by del x plus lambda del phi by del x. So it can be, whenever this is single relation, suppose single relation is there, then up to this stage you can get del f by del x. So, and also del f by del y, what will give? Del f by del y plus lambda del f by del phi by del y. Similarly, del f by del z equals to del f by del z plus lambda del phi by del z. So in place of this we can write del f by del s, del f by del y, del f by del z equals to 0. For shortcut, if we write f equals to f plus lambda phi. If 3, then we can write lambda on this, lambda 2 psi. Then also we can get lambda del psi by del x and so on. So this is equals to 0, this is equals to 0, this is equals to 0, this 0 means this is equal to 0. So our Lagrange's equation will be what? Del f by del x equals to 0, del f by del y equals to 0, del f by del z equals to 0. This will be the Lagrange's equation. Lagrange's equation for finding stationary points. In shortcut, you can write if f equal to like this, if f equal to like this. So these are the Lagrange's equation. By using this, we can find the stationary points for finding maximum or minimum value of a function of 3 variables, multivariables. Okay, so here now take questions for solving one by one, 2, 3 questions we will solve in this class. Okay, so first question is, here and rectangular box. So see the question. Open at the top. Have volume 32 cubic feet. Find the dimension of the box requiring least material for its constructions. Okay, so here we have to make a box open at the top. We want to make a box open at the top, rectangular box. Okay, and volume is volume is given 32 cubic feet, and we have to find dimension of the box. What is requirement? Least material will be requiring least material for its constructions. Material should be least. That is, surface area should be least, means minimum. Okay, so these questions can be solved also both by using both method, because there is given a single relation is given, so we can use the conversion of 3 variable function in 2 variable function, and we can use RS previous method also. But here for finding stationary points we can use Lagrange method also. After finding stationary points we can discuss in other way for whether this stationary point is maximum or minimum. So physical condition can be also used for finding nature of stationary points. So here solution. Box. So consider in this diagram just this type of box we want to make. So let x, y, z are the dimension. So let x, y and z are length, breadth, let x, y, z are length, breadth and height. X, y and Z are length, breadth and height are the dimension as length, breadth and height of box, then its surface is given by S equals to xy plus 2yz plus 2zx. Because for this box, xy is the area of face of the bottom face. Top is open, so single times, and remaining faces are 2 times. So rectangular box, surface of rectangular box. This is equation 1. And volume is given, and volume is 32 cubic feet. 32 cubic feet. That is, volume will be what? X, Y, Z equals to 32. So this is equation 2. Now here U is function of x, y, z, and x, y, z are connected by this relation. So single relation is there. So we can solve by Lagrange's method also here, and also by converting it in single variable, function of 2 variable, because we have to minimize, find the minimization, minimize the surface area for construction. Okay, list surface. So here, for stationary points, that is, for maximum or minimum of S, we have the Lagranges. We have the Lagrange's equation. Lagrange's equations as follows. What will be the Lagrange's equations? Here, this relation can be written as, how can we write this relation? Here we see that this can be written as function of x, y, z, and from here s equals to this function of x, y, z, equation 1. And this is relation, x, y, z are related by this relation, x, y, z equal to 32. So from here we can write phi x, y, z, relation between x, y, z, just like x, y, z transfer to left hand side, what? X, y, z minus 32. So x, y, z minus 32 equals to 0. This is equation 2. We can consider like this. So our phi x, y, z is equals to this, and f x, y, z equals to this. So this is our requirement, f plus lambda phi now. So is given as what? F plus so here we can write directly Lagrange's equation as follows. What? Del f by del x equals to 0, del f by del y equals to 0 and del f by del z equals to 0. Let f equals to f plus lambda phi. Let f equals to f plus lambda phi. Then del f by del s, del f by del y, del f by del z equals to 0. Here. Okay. This implies del f by del x. This. So del f by del x plus lambda, del f by del phi by del y equals to 0, del x implies del f by del y plus lambda, del phi by del y equals to 0 implies del f by del z plus lambda, del phi by del z equals to 0. This means this, if f equal to this. Now here, from here we can write equation del f by del x here with respect to x derivative of f equal to this f s surface area, this. So del f by del x, f means this with respect to x. So here y plus this will be 0, partial derivative, 2zx x, so y plus 2z. This is y plus 2z plus lambda of del phi by del x, del phi by del x, del phi by del x, this constant 0, x, so yz plus lambda yz equals to 0. Similarly, from here we can, with respect to y, so here x plus 2z, y with respect to x plus 2z, so x plus 2z plus lambda of, with respect to y, so xz equals to 0. Similarly, del f by del z, del phi by del z with respect to z, so here with respect to z, then this is 2y plus 2x, 2y plus 2x plus lambda of, with respect to z, that means xy equals to 0. Clear? This we get like this. Now these are the three equations, Lagrange's equations. So by using these, suppose this is 3, this is 4, this is 5. These three equations, 3, 4, 5 and 2 given relation. You solving this 3 relation, we can get stationary points. So solving very simple, because here we see that xyz equals to 32. So, or here lambda is what? Just try to find from this 3 equation value of lambda and just put the value of lambda here and we can get value of xyz. Okay, so for solving 2, 3, 4, 5, we can see that if you multiply it by x, then there will be xyz. If you multiply it by y, then there will be xyz. This is lambda, this is lambda. So these two quantity can be taken right hand side will be equal, and left hand side with that xy plus 2 From here we can get value. So see, solve. Our main target is what? Finding stationary points. So solve. Solving or multiplying 3 4 by 5 by 3, you can write like this: solving 3 and 4 as 3 is multiplied by x and 4 is multiplied by y gives, this is multiplied by x, this is multiplied by y, which gives lambda xyz, lambda xyz. So lambda xyz equals to lambda xyz equals to, here see, x multiplied, xyz, here y multiplied, xyz, so both are equal, so this is equal, transferring to right hand side, multiplying by y by x, so we can get minus what? xy plus 2z x, because multiplying by x, same here, xy plus 2zy. After multiplying, we get like this. These two are equal, so these two are equal, which gives what? Minus minus, so xy plus 2 zx equals to xy plus 2 zy. Here xy 2 zx equals to 2 zy implies x equal y. So we get x equal y by multiplying it by x, it by y, and we get this, so this 2 gives this x equal y. Now 4 into y, here xyz, and 5 into z. Also solving means when, okay, just you can do it in rough work as a, okay, so 4 into y and 5 into z gives, also lambda xyz equals to what? Minus xy plus 2zy equals to, also same value, second part, or you can write here also, and lambda xyz, see, then minus 2yz plus 2zx. This will give what? First we get what? X equal y, and here gives this minus minus plus, so xy equal to zy, x plus 2zy equals to here 2yz plus 2zx. So here we get this cancel out, so xy equals to 2zx implies here x cancel, y equals to 2z. So also we get this. These three equation, and also you can use this if we require. Here these three quantities are same, so lambda is not required, we can solve it. Okay, so y equal to 2z also, y equals to 2z. So this is our value, x equal to y equal to 2z. Now we can find the value where function is either maximum or minimum. So stationary points are given. Thus stationary points are given. So stationary points is given by x equal y equals 2z, and it can be used here 2, since x y z equals to 32. So here x equals to 2z, use here 2z, and y equals to also 2z, here 2z, and z equals to 32. So 2 into 2 4. So zq equals to 2 into 2 4. So zq equals to what? 8. Z equals to 2. Z equals to 2. If z equals to 2, that means implies here x equals to 4, y equals to 4, because z equals to 2, 2 into 2 4, so x equal to y equal to 4, 4 4 2. Okay, that is point is 4 4 2. That is stationary point is 4 4 2. So at this point surface is minimum. How can we? Because a stationary point may be maximum or minimum. So a stationary point, this is by Lagrange methods we get this is a stationary points, and this stationary points gives minimum value. So how can we determine it? So we can use previous method by converting it in the form of function of two variables. In place of z, you can write 32 by xy. So put here. Then s will be function of two variables, and find r, s, t, and rt minus s square at this point, maximum or minimum. We can find by discussion of rt minus s, sign of rt minus s square, and using the sign of rt minus s square and r square. That is mathematically, because here single relation is given. If single relation is not given, two relation is given, connected relation, then we can use physical condition or geometrical condition. Here, since single relation is given, so we can use previous technique for finding. Also physically, or we can see for the diagram that if whenever the box, if z increases, if z is very small, z increases from small to in the box, z in this direction. So z is small and then increase slowly. And when z is small, very small as 0, then the box having a base of big base, that is surface area will be also increase. surface area will be big, and when z increases in this direction, the base will be also base will decrease and surface area will decrease, and at after some stage when z increases, the surface area will be again start increasing. That means increasing greater value, then decreasing, and again increasing. That means there will be a stage where surface area will be minimum. At that stage, the value of x, y, z are given by 442. That is the dimension are 442. It is the geometrical discussion for finding nature of these stationary points. Also, for single connecting relation, we can convert it in function of two variables. Here, using 2, we can write as equals to xy plus, here z is common, so 2x plus 2y into z means from here z equals to 32 by xy, 32 by xy. So here we see that here only xy are there. So xy plus 2 can be common, 64, and divided by, so 1 by x plus 1 by y. So this is s. Now we can discuss about maximum minima at this point. Okay, so for that we require del 2s by del x square r. Okay, and s del 2 s by del x del y, and t del 2 s by del t square. We can get first time differentiate and then second time differentiate, we can get r. First time differentiation and with respect to y, and then with respect to x, we can get s. Also we can get t. Okay, so differentiation it first time with respect to x, so y plus, here see, x with respect to x, y, now 64, and 1 by x, this 2 with respect to x, so minus 1 by x square, minus 64 by x square, y minus 64 by x square. This is the first time differentiation. Second time differentiation with respect to x, again what will be the value? This is 0, minus plus 64 by x cube. Here also 2, so 2 into 64. 2 into 64. 2 into 64 means 8. 128 by x cube. So 128 by x cube. This will be the r, value of r. Similarly, you can find s1. First differentiate with respect to y and then with respect to x. And here 128 by y cube. Two time differentiation. First time we differentiate with respect to x, then what? This is first time differentiation with respect to x. Just differentiate with respect to y. Then this will be 0 and this will be 1. So s equal to 1. T equals to this. So in case when there is single relation, we can use this relation to convert it in as a function of two variables, and then find RST and use this stationary point. At this point, what is the behavior of this point? Just like this. So at 4, 4, 2, R equals to, means x equals to 4 and s equals to and t equals to. Okay, s equals to 1, 1. 4 into 4 into 4, 4 into 4, 16, 16 into 4, what will be the value? Here, one 128 upon 4 into 4 into 4. So this is 2. This is also 2. Okay. Clear? So R equal to 2, S equal to 1, T equals to 2. Now for deciding whether maximum or minimum, we see that RT minus S square is equals to 2 into 2 minus 1 equals to what? 4 minus 1 equals to 3 is greater than 0. 3 is greater than 0. Clear? 3 is greater than 0. But that is RT minus S square is greater than 0. Also R equals to 2 greater than 0. So RT minus S square greater than 0, R is equal to 2 is greater than 0. That is 4, 4, 2 is point of minimum. Point of minimum. You can write like point of minimum. Minimum is least. Hence, we can say the dimension of the box will be 4, 4 and 2. Thus, the dimension of box for least surface. Dimension of the box for least material. For its construction R x equals to 4, y equals to 4, z equals to 2. This is our answer. Length 4, breadth 4 and z 2 feet. These are the dimension for least. The dimension of the box for least material requiring for its construction. Dimension of box for least material for its construction are this. Okay. So here what we have done, finding a stationary point through Lagrange method, and for discussion whether this is point of maxima or minima, just we use this relation to convert it in function of two variable, and we use RS previous method RT minus S square and so on. And you can also discuss physically and say that whether this point is for minima or for maxima by physical condition or geometrical condition. Okay. So this is the solution of this question. Okay, now take another question. Here main thing is what? Main thing that for finding stationary points we can use Lagrange method, or also we can solve it by converting the main function in terms of two independent variables. That is, we are trying to reducing the independent variables. Number of independent variables must be least. In this question, so we convert 3 variable to 2 variable. So for 2 variable functions, we know how can we discuss about maxima minima by using rt minus s square and sine of r. Okay. So if a single relation is given, then we can convert 3 variable function to 2 variable function and we can use it. Okay. But for second question is related to show that the rectangular solid of maximum volume that can be inscribed in a sphere is Q. Okay, that means what? Rectangular solid in a sphere. We are having a sphere and we want to make a rectangular solid in the internal part of the sphere, and when the volume of the solid will be maximum, then the solid will be a cube. Rectangular solid means xyz are direction, their dimensions as and when this rectangular solid will be cube, that means xyz should be equal for maximum volume. So here by using Lagrange method, if we find stationary points and if we see that xyz are equal, then we can say that rectangular solid will be a cube. So here we can use Lagrange's method. Okay, so solution. So here just see the diagram that under a sphere just we are making a rectangular solid, because inscribed in a sphere. So sphere can be taken, any sphere can be taken. So very simple sphere, we know x square plus y square plus z square equals to r square. That is sphere of radius r. We can take that sphere. Center of that sphere is as the origin. So we can take dimension of the rectangular solid as, suppose like this, in this diagram, here this x, this is x, so this is 2x, so no, in this direction y, so here 2y, so in this direction here x, here x, 2x, so 2x, 2y, 2z can be taken as a length of edges of the rectangular solid, 2x, 2y, 2z, 2x, 2y, 2z, because here is the center. Origin is the center. So here y same value is can be taken here because the sphere will be like this. So we can take dimension as 2x, 2y, 2z. So let us suppose that the length, breadth and height of rectangular solid, let 2x, 2y, 2z be the length, breadth and height of the rectangular solid. Then volume is V equals to 2x into 2y into 2z equals to 8x y z. 2x, 2y, 2z be the length, breadth and height of the rectangular solid. Then volume is this. This is volume should be maximum. So this is question 1. According to the diagram. Okay. And circle is fixed. So let R be the radius of sphere. Sorry, sphere is fixed. So R be the radius of sphere. Then here center is 0, 0. So we can write x square plus y square plus z square equals to r square. This is the equation of sphere. This is the relation. One relation. Here V is function of x, y, z and this is x, y, z are connected by this relation. So for maxima or minima of V, the Lagrange's equation. Lagrange's equation are Lagrange's equations are given by del f by del y equals to x equals to 0, del f by del y equals to 0 and del f by del z equals to 0. Here del f by del x, here f equals to v plus lambda of v. It can be written, just you can also write like this, f of x, y, z, equation 1. Okay, from here we can also write like this, phi x, y, z equals to x square plus y square plus z square minus r square equals to 0. Question 2. So you can write f plus lambda phi. Here del f by del x equal to 0, del f by del y equal to f means f plus lambda phi. F plus lambda phi means you can write del f by del x plus lambda del phi by del x equals to 0. Same del f by del y plus lambda del phi by del x y equals to 0. Del f by del y plus lambda del f phi by del z equals to 0 here, not y, z. This is our basic rule for writing Lagrange's equation, where f equal to this. Function of x, y, z relation is this. So, we can get, just we are trying to find the stationary points where volume will be maximum or minimum. So, here just we have to show that if maximum volume, then volume maximum, and then the rectangular solid will be cube. That means dimension should be equal. That is x, y, z should be equal. Just try to find that value here. Del f by del x, f, this is at x, y, z. So del f by del x, that means what? With respect to x, 8 y, z. 8 y, z. Plus lambda here, del phi by del x. This is phi, this is this phi. So del phi by del x with respect to x. This fix 0, 0, 0, 2x. 2x equals to 0. Similarly, 8 with respect to y, so zx. xz. Lambda 2 with respect to y, so 2y equals to 0. Similarly, 8 with respect to z, that means xy plus lambda 2 z equals to 0. Just like this. Now for solving it, what is the rule? Using this 3 equation and this. That is this. We can find the value of x, y, z. So here we see that in this case, if this 3, this is 4, this is 5. Now just multiply it by, because x, y, z, 8x, y, z. So here multiply by x, multiply by y, multiply by z, then 8x, y, z, 8x, y, z, 8x, y, z, all are equal. So these all are equal. So we see that, so this is our, these are the Lagrange's equation. So we can solve 3 into x, 4 into y, and 5 into z will gives 8xyz equals to minus 2 lambda x square minus 2 lambda y square minus 2 lambda z square. At xyz equals to minus 2 lambda x square, minus 2 lambda y square, minus 2 lambda z square, all are at xyz. So, at xyz equal to this, this, this. From here we can see that minus 2 lambda, minus 2 lambda, minus 2 lambda. So, x square equals to y square equals to z square, implies x equal y equal z. That is 2x equal 2y equal 2z. Which implies that rectangular solid is cube. Solid is a cube. So, and in this diagram, if z is 0, then we get a rectangular sheet only, not rectangular solid, rectangular sheet. That is, volume will be 0. And as Z increase, the volume will increase. So, volume will be maximum in this situation. And in this situation, dimensions are, that is, length, breadth and height are equal. So, rectangular solid is a cube. Three sides are equal, so cube. So, this is using Lagrange's undetermined multiplier methods. Okay, stationary points, for finding stationary points, we use this, and then you can discuss about it. For maximum volume, if Z is equal to 0, then the rectangular sheet volume will be 0. If Z increases, then volume will increases. So, for maximum volume, the rectangular sheet solid will be cube. For maximum volume of rectangular solid, which implies that rectangular solid is a cube for maximum volume of rectangular solid. Okay. Now take another question. Here, use the method of Lagrange's multipliers to find the volume of the largest rectangular parallelepiped that can be inscribed in the ellipsoid x square by a square plus y square by b square plus c z square by c square equals to 1. Here, ellipsoid 3D diagram. In the inner part of ellipsoid, we have to make a parallelepiped. Parallelepiped means 3D figure. Just like parallelogram, you can trace by using a parallelogram. Parallelogram in a sheet can trace 3D figure, that will be parallelepiped. So parallelepiped, largest volume of largest rectangular parallelepiped means maximum. Largest means maximum. So parallelepiped, volume of parallelepiped will be maximum, can be inscribed. So here we have to find volume, maximum volume. Means in the ellipsoid we will make a parallelepiped. So we have to find the maximum volume. Just in the ellipsoid, if we make a parallelepiped, then there will be maximum volume. So maximum volume we have to find. Okay. So here, for finding maximum volume, just we can use Lagrange's method. Very simple. Just here we can see also a function is given and a relation which will connect the variable of the function. Here, suppose we inscribed a rectangular parallelepiped within a ellipsoid. So here maximum, what should be maximum? Volume of the parallelepiped. So that will be our function. Maximum or minimum. So here also we suppose that because parallelepiped ellipsoid is given x square by a square plus y square by b square plus z square by c square equals to 1. So that is just like ellipse is rounded or revolving about an axis up to 1 times. That is the diagram of ellipsoid. So here diagram dimension of parallelepiped we can take same as, because here diagram like this, ellipsoid will be this type of diagram, ellipsoid. Okay, and parallelepiped will be like this. So here origin is center of the ellipsoid. So we can take dimension y, 2y, same 2x, 2y, 2z and so on. So we can take let 2x, 2y and 2z be the length, breadth and height, na? Of the rectangular parallelepiped. Length, breadth, height of parallelepiped. Then its volume is also, this is V equals to 2x, 2y, 2z, 8x, yz. Equation 1, it can be written like this, fx, yz, same type of relation like in the previous question. Okay, 1 and equation of ellipsoid is x square by a square plus y square by b square plus z square by c square equals to 1. Okay, this is given. It can be written like this, phi xyz equals to x square by a square by plus y square by b square plus z square by c square minus 1 equals to 0. Phi equal to this. Just like in the previous questions, here a, b, c are equal. Okay, so this is equation 2. If f equals to f plus lambda phi, then Lagrange's equations are del f by del x equals to 0, del f by del y equals to 0 and del f by del z equals to 0. Gives, here we see that what? Del f by del x plus lambda del phi by del x equals to 0. Similarly, we can write fx plus lambda phi x, in short fy not x, y. This short, in short, we can write like this, z equals to 0 with respect to z partial derivative this. Now differentiate it. Del f by del x means same as previous question. X, so 8yz plus lambda into, here what will be the value? Del phi by del x. Del phi by del x 2x by a square. 2x by a square equals to 0. Similarly, 8zx plus lambda 2y by a square equals to 0. And here, with respect to z, so xy plus lambda 2z by a square equals to 0. Not a square, here b square. Here b square, here c square. C square. So similar type. Del phi by del s, del phi by del y, del phi by del z, these are the values. Okay, now here we have to find stationary points. So for finding stationary points, we can see that if we multiply this equation by x, by y, by z, then x square by a square, y square by b square, z square by c square, and just add this, then 2 lambda of 1 equals to this. So here equation 3, equation 4, equation 5, 3 into x plus 4 into y plus 5 into z gives. This means what? Equation 3 is multiplied by x, equation 4 is multiplied by y, equation 5 is multiplied by z, and add up this. Then 8xyz, 8xyz, 8xyz. Okay, so what we will get? 24 xyz, xyz. Adding this xyz, xyz, xyz. So 2 lambda, 2 lambda, 2 lambda common, x square by a square, y square by b square, z square by c square. So plus 2 lambda x square by a square plus y square by b square plus z square by c square equals to 0. Now using this relation, this is equals to 1. We have 1. So implies 24 xyz plus 2 lambda into 1 equals to 0. So here lambda equals to minus 12 xyz. This is the multiplier lambda. Lambda equal to minus 12 xyz. So we can use this lambda here and can get the value of x, y and z. Clear? Now using this lambda in equation 3, okay, using the value of lambda in equation 3, we get in equation 3. So here 8yz plus lambda means minus 12 xyz into 2x by a square equals to 0. So here we see that yz we take in common not equals to 0. So 8 minus 12 x square, 12 into 24, 12 into 2 24 x square, yz is taken common like this, yz this upon a square equals to 0. Yz is not equals to 0, so 8 minus 24 x square by a square equals to 0. From here we see that x square equals to 8a square by 24 equals to a square by 3. So x equals to, here x equals to a by root 3, implies x equals to a by root 3, x equals to a by root 3, x equals to a by root 3. Clear? X equal to a by root 3. Similarly from 4 and 5. Similarly from 4 and 5 we get y equals to a by root 3 and z equals to a by root 3. So all values are not a, b by root 3, c by root 3. So stationary points is x, y, z. Okay. So the stationary point is a by root 3, a by root 3, a by root 3 is this. Okay, and in this stationary point, and here we see that also when z equal to 0, then parallelepiped, the volume, okay, volume will be 0 as a rectangular shape, and when z increases, then volume will increase. So at this stage, this point, that is at this dimension of parallelepiped, the maximum volume is given by volume is equals to 8xyz. So 8xyz means 8x means a by root 3, b by root 3, c by root 3. Okay, so 8abc by, what will be the value? Here 8abc by 3 root 3. So this is our answer. Volume, maximum volume, 8abc by 3 root 3. 8abc by 3 root 3. Okay. So this is the technique for solving. Just previous question and this question mostly same, as same, because here ABC are different. Okay, left side there was sphere. Here maximum volume is this. Okay. So Lagrange's multiplier method means just we are trying to find stationary points by using the Lagrange's equations. And at that point, for taking decision, you can convert the function as a two variable function by using the relation. Whenever a single relation is given and RT minus T square is greater than and R is greater than minimum or less than maximum, you can use that for deciding maximum or minimum. But also physically you can decide. If in the questions it is given that to find the maximum value, find the minimum value by using Lagrange's main theorem, just you use the Lagrange's formula and get stationary points. That is the maximum, that is the minimum. Because in the questions it is given that find maximum value, find minimum value. That is at that point function will having maximum value or minimum value. So you can use Lagrange's method. Okay. Now here one question is more here for two relation is given here. Okay. Up to now we are solving questions where single relation was given. Now here two relation is given. That is, if u equal to ax square plus by square plus cz square, this is the function. Okay. Where x square plus y square plus z square equals to 1 relation, and Lx plus My plus Nz equals to 0, another relation. Then prove that side. Here, prove that stationary values of u. U means what? Function of three variables. Stationary value means either maximum or minimum value of the given function is given by an equation. Means value of u can be found from a relation that will be a stationary value for the function. So this type of questions also can be solved by finding the value of lambda and put the value of lambda in any of the relation for getting the required relation. Okay. So we will solve these questions now. See here. Solution here given that u equals to ax square plus by square plus cz square. Clear? Here this is given. Equation 1. And or we can write like this, where phi x y z, because here it is given also that x square plus y square plus z square. So where x square plus y square plus z square equals to 1 and Lx plus My plus Nz equals to 0. This and this. These are given. Okay. In the question it is given. Now we have to find a relation having u which will give a stationary value for the function u. Okay, so we can use Lagrange's multiplier method So here we can write phi xyz equals to x square plus y square plus z square minus 1 equals to 0. And here another relation psi xyz equals to lx plus my plus nz. This is equation 2 and this is equation 3. Okay, these are the given. Here two relations are given. This is function of 3 variable, u is function of 3 variable f x y z. So here we can also write like this. This is function of x, y and z. Equation 1. This is equation 1, 2, 3. Function of x, y, z. X, y, z are related by this two relation. Here phi x, y, z means this. This equals to 0. Clear? Phi x, y, z means this. Psi x, y, z means this. Clear? Now, if f equals to f plus lambda 1 phi plus lambda 2 psi, then here two relation, so we will use this relation, then Lagrange's equation, then we can write f as a function of x, y, z equals to f means this ax square plus by square plus cz square plus lambda 1 phi means this x square plus y square plus z square minus 1, lambda 2 means, and psi means this lx plus my plus nz. Clear? This is fx. Lagrange's, we have to find a stationary value of u. For here, for finding multiplier, value of multiplier, we can use Lagrange's equation. R. What? Del f by del x equals to 0. Now del f by del x means f differentiated with respect to x. So we get what? 2ax, and this two are 0. Here 2x, 2 lambda 1 x, and remaining are 0. Here lambda to L, lambda to L. This is equals to 0. Similarly, del f by del y equals to 0. So what we get? Same. 2ay. No, here a not a, b. Okay, ax square. No? Yes. 2by plus again 2 lambda 1 y plus lambda 2 m equals to 0. Similarly, del f by del z equals to 0 implies what? 2cz plus 2 lambda 1 z plus lambda 2 m equals to 0. So these are the equation 1, 2, 3. This 4. This is equation 4, 5, 6. Now for finding a stationary value of function u, we can find the value of multiplier in terms of u. By using multipliers, we can find the value of x, y, z, that is as a stationary point in terms of u, and then we can put that value in this relation for getting our required equation, because in the required equation there is given L square, M square, N square upon A minus U, B minus U, C minus U. That can be found. That relation can be found because here element is here. If we can get x, y, z in terms of lambda and element, then we can get that type of relation. So our required relation we can get. So here for solving, see, in this relation, because we are trying to solve finding value of x, y, z from this and this relation and this relation, because there are two connecting relation. So this two relation we used, and also this 5 can be used for finding a stationary points. Okay, so here see that L, M, N, so Lx, My, Nz, if we add this, then lambda to common, Lx plus My plus Nz, can we get that is equal to 0. Here x, y, z, here x square, y square, z square, x square, y square, z square, 2 lambda 1 common, that will be equals to 1, so we can use it also, these two can be used. Here ax square, by square, cz square, that is equals to u, we can use here u, very simple. So multiplying 4, 5, 6 by x, y, z and adding. So multiplying 4, 5 and 6 by x, y and z respectively, and adding, we get, just multiply and add. So 2 common, ax square, by square, cz square. So 2 ax square plus by square plus cz square, 2 lambda 1 common, x square plus y square plus z square, 2 lambda 2 common, Lx plus My plus Nz equals to 0, right side 0. So using 2 and 3, this is equals to 1, this is equals to 0, 1, 0 implies this is equals to u, using 1 to 3. So 2u plus 2 lambda into 1 into 1 plus lambda 2 into 0 equals to 0. We are using 1, 2 and 3. Using 1, 2 and 3 we get this. From here just see, this is 0, here 2 common, 2 is not 0, so u equals to minus lambda 1, that is lambda 1 equals to minus u, lambda 1 equals to minus u. Clear? So here multiplier, the value of the multiplier lambda 1 equals to minus u. So this minus u can be used here in this plus. Okay? Clear? Lambda 1 equals to minus u we can use here. Now, put lambda 1 equals to minus u in equation 4, 5 and 6. In 4, 5 and 6. We get like this. We get in 4, this is 4. So here 2ax plus 2 lambda 1, 2 lambda 1 minus u x plus lambda 2 L. Clear? Is equals to 0. And also in 5, 2by plus 2 minus u y plus lambda 2 m equals to 0. And also in this equation, 2cz plus 2 minus u z plus lambda 2 n equals to 0. Okay. Just we use this lambda 1 equals to minus u here. Now from here just find the value of x, y and z. We can write it. Here x only x, here only y, only z. So from this relation, see here x can be taken common. So 2a minus 2u, 2a minus 2u, we can write x equals to, from this relation, we can write x equals to minus lambda 2 L upon 2 a minus u. Similarly, from this relation, y equals to minus lambda 2 m upon 2 into b minus u. From this relation, z equals to minus lambda 2 n upon 2 c minus u. Okay, this from this three equation we can write the value of x, y, z. Here in terms of lambda 2, lmn and 2a minus u, b minus u, c minus u. For our relation, for our record relation, here a minus u, b minus u, c minus u is also there. Okay, so for getting that relation, this is stationary values. This is the stationary values x, y, z in terms of u. And stationary value of u is given by this values, and this value can be used in any of the relation. So for getting that relation, we can put this values here. We can get relation. Okay. So here see that our main requirement is equation. For getting the required result, we can write now, putting the values of x, y, z in third, we get because we want that relation. So here in place of x, L x means this minus lambda to L upon 2a minus u plus m into minus lambda to m upon 2b minus u n into minus lambda to n upon 2c minus u equals to 0. So here right hand side 0. So here minus lambda 2 by 2 minus lambda 2 by 2 minus lambda 2 by 2 can be cancelled out. So we get what? L square upon a minus e plus m square upon b minus e plus n square upon c minus e equals to 0, which is required relation giving a stationary values of u. Okay, so this is the required relation which gives stationary values of u. So Lagrange's method is useful for finding a stationary value of the function as required in questions for finding what value we have to find. So you can use Lagrange's multiplier method for finding a stationary value and discussing about whether maximum or minimum by using physical or geometrical condition, and also converting if there was single relation, connecting relation, then you can convert main function in terms of two function and you can use previous method. Okay. So now I'll give some question to you for solving, because this method is very important. So just solve some these questions by using any of the method. Because this 10 questions are for your practice. Okay, just assignment work, you can suppose. All the questions are very important. Okay, just you have to solve all these questions in your copy. Try to do all the questions by any of the method as required. In some of the questions it may be required for using Lagrange's multiplier methods, and maybe the converting function into variable functions and using rt minus s square, finding value of rt minus s square, you can decide whether the value of function is maximum or minimum. For if in any of the questions it is required to finding the maximum value or minimum value, just first test rt minus s square. The sign of rt minus s square is greater than 0, then r less than 0, then maximum, r greater than 0, then minimum. And it is also useful for using Lagrange's multiplier method. Okay, so Lagrange's multiplier method is also useful for stationary points, and this type of relation, just in the previous questions we are using relation involving u means main function, so it may require by using Lagrange's multiplier method. Okay, so do all these questions in your copy. Okay, try to solve by using other books also, Grewal, HK Das, and so on. So do all questions in your copy, okay?